Hello, this is AP Calculus BC class with Mrs. Ryu. Let's get started with the chapter 9.1 sequences. So what is a sequence? Okay, let me underline the sentences here. It says a sequence is defined as a function whose domain is the set of positive integers. So if I have a(n), okay, n is a positive integer, okay, and he said it is a function, so that means it has some kind of a pattern. So sequence, I would define it as a list of numbers, okay, but not like a random numbers. It has a pattern, so let's write down with a pattern, okay. Then each number is called a term. So we can say that first term, second term, third term, okay? Let's find the terms of the sequence. an is 3 plus negative 1 to the nth power. We are going to plug in some numbers, like positive integers. So a1 is 3 plus negative 1 to the first power. So that is 2. A2 is 3 plus negative 1 squared. So that is 4. A3 is 3 plus negative 1 to the odd number again. So that is 2 again. So this sequence goes 2, 4, 2, 4, 2, 4, infinitely repeating. Okay, C, I'm going to skip B. The terms of the sequence of Cn, it looks like this. So let's plug in the numbers. C1 is 1 squared, 2 to the first power minus 1, so that is 1. Okay, C2 is 2 squared, 2 squared minus 1, so that is 4 over 3. C3 is 9, which is 3 squared, 2 cubed minus 1, so that's 9 over 7. Okay, so the sequence of C goes like 1, 4 over 3, 9 over 7, okay. So now let's look at the limit of a sequence. By the way, the graph of a sequence looks like this, like a point, okay. It's not a line or the curve. It is just a bunch of points because, again, the sequence is a list of numbers, okay. The limit as n goes to infinity of the sequence an, if that is a certain number, like L, okay, it's a defined number, then we say that the sequence converges to L, okay. If the sequence doesn't converge to L, then the sequence diverges. Mathematically, we can see that the difference between the sequence and L, okay, so right here, the difference between the sequence and L, so that's the absolute value of an minus L, is getting smaller and smaller and smaller. So if that is even smaller than epsilon, that's called epsilon. Epsilon means just some small number, okay. So the difference is very, very small, then we say that the sequence converges. Now let's look at the properties of the limits of sequences. If limit of an converges to L, the limit of B converges to K, If we add and subtract the sequences, that means we are adding and subtract the L and K. If we multiply by a constant to the sequence, that means we are multiplying the constant to L. If we multiply the sequences, that means we are multiplying L and K. If we divide, that means we divide L and K. Example number 3 says determine whether it converges or diverges. So AN is the sequence that we did previously. It was a 2, 4, 2, 4, 2, 4 sequence, right? So the graph looks like this: 2, 4, 2, 4, 2, 4. Okay, it keeps going. Okay, so as we see the graph, it diverges. Okay. Bn said n over 1 minus 2n. So can we find some terms of the sequence? So B1 would be 1 over 1 minus 2, which is negative 1. B2 is 2 over 1 minus 4, so that is 2 over negative 3. B3 is 3 over 1 minus 6, which is 3 over negative 5. So it's kind of hard to see that whether it converges or diverges. So let's do it in a different way. We're going to take a limit. N goes to infinity. N over 1 minus 2n. So n is getting larger and larger. So it's going to be infinitely large. The denominator says 1 minus 2 infinity. It's something like this. So infinity over infinity doubled is subtracted from 1. So in this case, we can use Thales rule because we have infinity over infinity. So let's take a derivative of a numerator and the denominator. So limit as n goes to infinity. N derivative will be 1, right? And 1 minus 2n, let's differentiate the denominator. That's negative 2. So the answer is it converges to, I'm going to write the answer here. It converges to negative 1 over 2. Example number 4 said, show that the sequence whose nth term is the AN converges. Okay, so instead of making a list of the sequence, we are going to see if we can use the L'Hopital's rule. Okay, if I have a limit n goes to infinity, n squared 2 to the nth power minus 1, it has some kind of like infinity over infinity form. So yes, we can use the L'Hopital's rule, yes. But before we use the rule, let's check. N squared, if we graph this, then it is a parabola, right? So it goes up like that. I'm going to change the color. Okay. And the denominator, the graph looks like, okay, it is an exponential function, 1 unit down, so it should look something like this. So which one goes up faster than the other? My assumption is the exponential function, but let's check. Okay, we are going to differentiate the top and the bottom. So n squared, the derivative is 2n. 2 to the nth power minus 1, the derivative is log 2 times 2 to the nth power, and the minus 1 is gone. Now it's another infinity over infinity form, but it's a little different now. The numerator is linear, okay, and the denominator, it goes up like this, okay, exponential. So I'm pretty sure that the denominator goes faster than the numerator, but let's apply the L'Hopital's rule one more time. So that goes, I'm gonna rewrite it, n goes to infinity, 2n, the derivative is 2, okay, and the denominator is log 2, and you have another log 2, so that's squared, and 2 to the nth power. So now we can say that it converges to 0. Hey guys, make sure that you wash your hands and wear a mask. I miss all my students. Bye!